Hi, welcome to the hypothesis testing talk, and we're going to talk about how to make some p-values. Firstly, are you ready for this? Make sure you know what simple linear regression is and how we estimate the parameters in a simple linear regression. Specifically, what do we minimize to estimate the parameters? Also, make sure you know what blue stands for. If you don't know these things, just go back to the simple linear regression talk just a couple days ago. Okay, so today we're going to talk about hypothesis testing. So what I'm showing here in these two panels are two sets of data with their regression lines plotted through the data. And if you eyeball it, you can tell that panel A's data and model fit doesn't look as good as panel B, so we need a way of assessing this. There are 5 parts to the hypothesis test. If you pick it apart, there's the null hypothesis, the alternative hypothesis, so we'll use this HO, notation for those two things. The test statistic and p-value, they kind of go hand in hand. The rejection region, and then finally your conclusion. So the null and the alternative. So the null is typically what you want to disprove. So if I were running a test to see if my boyfriend was cheating on me, my null would be what I want to disprove. So I would hope he wasn't cheating on me, so that is my null. And the alternative is typically what you want to be true. So your alternative is my boyfriend isn't cheating on me. So then hypothesis testing takes on a bit of a pessimistic view of life. You assume the worst, you assume your null is true, and you collect data and you compare your data to your null hypothesis and you say, how realistic are these data? So assuming the null is true, my boyfriend is cheating on me, how likely are my data? So in the first case, he buys me presents, he emails me throughout the day, he cooks me dinner and tells everybody how awesome it is that he's dating a biostatistician. Who wouldn't? Well, if he were cheating on me, these things wouldn't be very likely. So in this case, I would reject the null in favor of the alternative. On the other hand, if he stays out late, never says anything nice to me, and he keeps talking about his fun female coworker, and he has lipstick on his collar, how cliche. Well, if these are my pieces of data, if he were cheating on me, these things are pretty consistent. So I fail to reject the null hypothesis. Now note how carefully worded that is. I said I do not reject the null. We never accept the null. So we fail to reject it, but we never accept it. So that's a really important thing. If you're ever doing any type of analysis and the p-value is the end game, even if your p-value is really big, you can't then conclude that the null is true. And we'll get to why big p-values mean failing to reject the null in a second. So for this study example I've been using, reaction time and how it's associated with age, this was our model. Reaction time equals beta naught plus age times beta age plus epsilon. So there are different types of hypotheses you can run. So I'm going to focus on beta age. This is my parameter of interest. I want to know if there's a linear relationship. So the two-sided hypothesis is, I'm almost confident enough to say that it's 100% across the board what statistics software does. R definitely does by default. SAS does by default, from if my memory serves. And it's just typically what we do. And what it tests is as age increases, right, so the hypothesis is that as age increases, reaction time changes. So we're not so confident that we can say reaction time will increase or reaction time will definitely decrease. So we kind of leave it open. So the null is just that the slope is 0. And then the alternative is that the slope is either positive or negative. So rejection of the null means the slope is positive or negative. So typically if you reject the null, in this case, you then look at the sign of your parameter beta to determine the relationship. A one-sided hypothesis test is almost always what we do in imaging analysis, if you're using imaging analysis software. And in one sense, it kind of doesn't make sense. But on the other hand, if you think about, for example, fMRI data, typically you're comparing two tasks. And if your activation is such that, say, your faces, if you're testing faces versus houses, you did a face-house task, just knowing that faces were different than houses, that's kind of not enough information. We're actually interested in places where the face activation is larger than house activation, and that's different than where the opposite is true. So in some sense, one-sided hypothesis test makes sense in imaging because the directionality has a very different interpretation. So going back to the age example, we might assume that since this is reaction time, that the slope would be positive. So you always set your alternative to what you want to show. So a positive slope would mean as age increases, reaction time increases. So again, alternative hypothesis, what we want to show. The null hypothesis is what we hope isn't true. So in this case, rejecting the null only concludes a positive slope. So you get a more specific result when you use a one-sided hypothesis. And again, this is typically what is used in fMRI software, or just, I would say, generally in imaging software. Next up, we need a test statistic. So we need to somehow take this parameter beta and see if we can, well, we need the p-value. So before we get to the p-value, we need to be able to describe our parameter using a distribution. So I'm not going to go through it. We are going to assume today, we haven't made this assumption yet, but I'm going to assume the errors are distributed normally. So if the errors follow a normal distribution, it turns out you can show that beta hat age follows a normal distribution with a mean beta age and a variance equal to this variance of beta age, which, if you remember the linear regression lecture, that equation is in your head. It's x transpose x, the inverse of that, times sigma squared. So we know what x is, that's our design matrix. We do not know sigma squared. So since we don't know sigma squared, if you recall, what we did in the simple linear regression is we put a hat on it. So we're going to have to use the estimated variance of our parameter estimate. So that then leads to our t-statistic, which looks like this. So it's our beta hat age over the estimated variance of the parameter estimate for beta hat age. I'm not worried that you know the specific equations for these two things. This will be easier to understand once we cover contrasts, and that's coming up. So just for now, this is the structure. All I want you to know is we took a normally distributed thing, and we divided it by this estimated variance, which just so happens to follow a chi-square distribution. So roughly, I've glossed over a few things, but if you have something normal divided by the square root of a chi-square, it's a t. There's another thing in there with the degrees of freedom. And the degrees of freedom on the t distribution are n minus p, where this is the same as the degrees of freedom on the residual. So you'll remember when we were estimating sigma hat squared, in our simple linear regression, we had to divide the sums of squares by n minus p. And that is directly related to this n minus p. So whatever you divide that by is going to match your degrees of freedom on your t-statistic because they are related. And n is the number of subjects, p is the number of parameters in the model. So if I had 20 subjects and this model had 2 parameters, n minus p would be 18. So p-values for a one-sided hypothesis. So now we're doing great. We have a statistic and we have a distribution that the statistic follows. So we can compute a p-value. So given the null is true, how likely is it to obtain a value more extreme than our statistic? This is the definition of a p-value. So this first part, given the null is true, means we're going to work with this null distribution, this pessimistic view that nothing's happening in our data. And I'm going to start with the one-sided test, that beta age is greater than 0. So I'm going to assume there are 22 observations, simple linear regression, 2 parameters. So the null is a central t-distribution with 20 degrees of freedom. If you've never heard of a non-central t-distribution, no worries. This is just the t that you know. a non-central won't come into play until we talk about power. So here it is, note, centered at 0. And what you do is you slap your statistic down on this distribution. And let's say my statistic, my beta hat over square root of the variance hat of beta hat is right here. It's 2. So we assume the null is true. So under my null distribution, what is more extreme? What is the probability of observing my statistic or something more extreme? More extreme is always in the direction of your alternative. In this case, my alternative is greater than 0, so I'm going to move away from 0, which is this area right here. So this is more extreme. Now for the two-sided hypothesis, it looks like this. More extreme is either way away from 0, on the positive end or on the negative end. So this is just the negative of your statistic, and then you compute the upper tail probability. So you should be able to see that there is a relationship between the p-value for a two-sided test. So both of these I'm showing you are using the same test statistic of 2. So the p-value here compared to here, what's the difference? It's twice as big. Quick story. Once I was helping someone, I won't say who it was, and they ran a test and the p-value was 0.08. And I was like, oh, sorry. And the person said, well, it's a two-sided test, so really my p-value is 0.04. Suddenly, they were assuming that a priori they were going to run a one-sided test. If you're going to run a one-sided test, you must declare this ahead of time. You can't suddenly decide to do it because your two-sided hypothesis test p-value is, 0.8 or 0.9, something that when divided by 2 is going to get you below 0.05. Okay, notes about the p-value. The p-value is not the probability that the null is true. It is, again, this conditional probability. Assuming the null is true, observing my statistic or something larger. Therefore, 1 minus p is not the probability that the alternative is true. Right, so the rejection region, we have to choose a threshold, and a p-value is considered to be significant if it falls below that threshold, alpha, and typically we use alpha equal to 0.05. So you can think of hypothesis testing as leading to this 2 by 2 table. This is your result, or this is the truth. Either the null is really true or really false. So an oracle has come and told us. And this is your decision based on your statistic. Now, if you reject the null and the null is false, way to go. If you accept the null and the null is true, that's great too. If you reject the null but the null is true, that is a type 1 error. So our threshold alpha that we choose is that type 1 error. So if I choose 0.05 as my threshold for my p-value, that means that if the null is actually true, I only have a 5% of accidentally declaring it to be, rejecting the null. And likewise, there's another error when you accept the null and the null is false, and that's a type 2 error, which is beta, and 1 minus beta is power, which we will get to power another day. Right, so I'll just say this, power is 1 minus beta. The ideal situation is low alpha and high power, but it turns out power is directly related to alpha, so increasing alpha tends to increase your power. So you increasing one type 1 error controls another type 1 error. It's like a teeter-totter. One gets better, one gets worse, but you can't make them both great. Unless you can increase your sample size. So just all you guys have to do is plan studies with more subjects. Then you can have the best of both worlds. All right, that's it. Again, reminder, join the Facebook group, follow on the Tumblr, or you can follow me on Twitter. That's it. Thanks again for coming. Hope you're enjoying these, and I'll talk to you next time.